now it's recording.
Oh, okay.
Yeah, I think it fell when it dropped.
So the basic thing is the least F value node is off by at most C from the normal A star heuristic. Any other questions you want? Does it make
I was
sense?
running through an example. So it says how far the solution bound will be from optimal.
Yeah. How far meaning how off is it from G star?
The absolute value.
And we are saying that it will be off by at most C. Absolute value of the goal node found by A star will be less than or equal to G, A star plus. If they ask how far is it off, then we can say it's C.
I was just trying to think of an example where it expands and actually gets off by C. I thought of an example would be C
Yeah,
minus 1.
it's very easy, right? You just take this example and just put H equal to H equal to 3 here for this goal node. Okay, this is a goal node, and we say H equal to 3 instead of H equal to 0. And we put another goal node with some 10 and not 10. We need to put, so let us say this H cost is E. Let us say this is also a goal node. Then the way we say is that here the H value is 0, let's say. Then what happens is, at certain point in time you will have these two nodes with F value 7, okay? And in worst case, in tie breaking you will choose this node and turns out G is 7, and you will miss this guy whose G is 4, and this is the optimal solution.
So for that was also the test question. It was the very first one, 1A, and it says for the blind search you would use IDDF. Why wouldn't you use the breadth first search for that?
For the first one,
Yeah.
I think it was the C3PO one.
Yeah.
I think it's because you're trying to preserve memory.
Yeah.
And IDDFS uses linear memory. BFS uses exponential.
Okay. Okay. Thank you.
You can probably explain.
Yeah, right here. It's because C3PO
First question.
has very little memory. So,
Which one is it?
It was just the very first one. So, this one.
Oh,
They said it has to do with the memory.
do you recommend to E3?
IDDF uses linear.
and guarantees optimality. But yeah, it's this line right here.
Wait, you're going HRCSCS, you're going, what would you replace it?
It needs to be like IDDFS has the optimal like
So
breadth
we are
search.
basically
but
trying to
uses
solve the
depth
first
search
question
memory.
of last terms, midterm.
As Tom says, he has a low battery. Like maybe the runtime like BFS is too long. Who knows?
Oh, because that's
Never gonna get it.
Let me just.
Is that what happened in the movie? Were you doing like ID BFS and got lost in it?
disability. Consistency, quiet, so
So it basically says that it doesn't have a lot of memory, but it has time, and it wants to find the optimal solution.
Well, it says it's running low on battery. That to me implies it's a low on time as well. But, maybe that's just interpretation.
Yeah, so it definitely doesn't have memory, so we can't do anything like breadth first search. Now, within the given memory, you have to make sure that whatever the best you can do, you should be able to do. I think the battery is more with respect to how many steps the robot should take or will take, instead of how much time it spends on finding a path. I think it is assumed that finding a path doesn't really require a lot of energy, but taking a step does. Actually physically moving. I think that is an assumption. So, in such situation, which of the blind search methods? Basically, what are the blind search methods? DFS, BFS, and iterative deepening, right?
Is uniform cost blind search? Uniform cost, is that a blind search?
Uniform cost is also blind search. Yeah, whenever there is no edge, it's a blind search. Yeah, only thing here is we don't have memory. BFS or uniform cost search, all these will need exponential memory, right, in the worst case. And only DFS is the one which runs in linear memory of the methods that we study. So which one do you recommend? And you definitely want to find optimal path. Simple DFS will not guarantee you optimal path. So while trying to follow that path, the robot may die out of battery. So, and we definitely know that we need some variation of depth first search because we don't have memory. So that leaves us only one option.
Yeah.
Identity.
Do you think about it, it also increases the complexity, expanding?
Yes, but that's what it says, right? They have time. Fortunately, however, next movie starts until a month or so. So they don't have problem with respect to time. Any other questions?
In A-star graph search, a heuristic is admissible, but suppose it's inconsistent, still it will be optimal, right?
Yeah, so if you want it to be optimal, you need to basically have the mechanism where you will do the extra checking of whether you have found a better path or not to an existing closed list node. If you do that, it's guaranteed.
So that means you need to keep on checking the closed list also.
Yes, yes.
So if
In A-star graph search, we always check the closed list for duplicates.
Yeah,
But what we do, whether we just ignore afterwards or we do further checking like whether we found better path or not,
better cost.
depends on which kind of heuristic you are given.
So when you're doing recursive and progression and regression, can you quickly explain?
This is which one?
That's not on the test.
Oh, that's
Oh,
not in the test.
Regression.
Oh, not at all.
Those are last year's midterm covered more topics before it would be the first test.
Okay, that's cool.
Yeah.
What's the difference between a state-space representation and a state-space representation?
Yeah, so that's a very good question. So, whenever you are given a problem, you can design a state as you wish, right? You can put all sorts of things. The minimal state space representation basically asks for a representation which takes minimum number of bytes, to be precise. So, let us say you have this robot where roaming around in a grid-like scenario. So, what do you want to keep track of in such situations in a robot state? You will obviously have its location. You will have its current, let's say, what is the energy level of the robot, and if it can actually travel at multiple speeds, you will need to keep track of what is the current speed, what is the probably current acceleration, things like that. So it all depends on what kind of an environment you are working in. And you don't want to keep anything more than the minimum required. Let us say our goal is all about taking that robot to a certain location. Then and there are so many things like whether a robot is holding some package, not holding some package, all sorts of things. But for your ultimate goal, it doesn't matter whether it's holding a package or not. So you don't want to keep extra variables such as whether the robot is currently holding a package or not, because it never matters for your problem. So what kind of a state space representation you are coming up with has to take into account what problem you are trying to solve. And you want to keep the number of bytes for each state as minimum as possible.
So minimal would be like the very base you need to solve the problem,
Yeah.
where it's just the regular state space things that might also just be nice to have.
No, you don't want to keep anything extra. Like what?
For regular state space, the minimum is like the very base that you need to solve the problem.
Yes.
But there's not minimal, just the state space representation would be also information in addition to the.
Yeah, that's what all the package kind of, what is the weather when I am in this location.
So the things that they're, the things that are being stored, would they aid in solving the problem, or are they just things that are nice to have?
Yes. So we don't want to, keep any extra information which are not helping us in solving the problem.
In homework 2 we had this question 7. So
Okay.
this is about two insects in a state space,
Okay.
and the question is what is the size of the state space?
Yeah.
And the minimal state space representation doesn't include k as a value. However, the size of the state space is mn power k. How do we find that?
So the question is, we are controlling k insects, each of which has a specific target ending location. No two insects may occupy the same square. Yeah, so basically there are k insects. So, and each one can be in any one of these m into n locations, right?
Okay.
So, insect 1 is at one of these locations, and when this is true, insect 2 could be any one of the mn locations, and so on, right? So, it becomes mn power k, assuming that same location can hold all the k insects. Oh, is it given?
Yeah.
Okay, then the answer won't be right. Yeah, no two insects may occupy the same square. In each time step, all insects move simultaneously. Yeah, then you have a different problem, right? Basically, then you have a situation where if you know combinator X, the total number of possible states is m into n, and you need permutations for k's. Or other way saying, who are comfortable with C notation, you choose k places where these insects will be, and there are several orders in which all this can hold, basically into k factorial. Both of these are same.
So the answer is not? So the answer is?
Yeah, if it's mn power k, then it's wrong, clearly. It will include cases where all the insects are in the same place. Let us say the first guy is in 1 into 1, second insect is in 1 into 1, and so on. That is also counted in this formula. But if we want that no two insects should be in the same place, then we will actually have this.
So
Is that even an answer?
No, that's not an answer.
Which? Question 7.
Okay. Yeah, that's why this confused me. So.
Yeah, that's why the whole homework confused me. All 27 questions. What does that even mean though? Underscribe?
Permutation.
Permutations. Permutation P times K. It's weird.
Oh, okay.
Do you know what a tuple is?
Yeah, just an ordered pair.
What?
It's like an ordered pair.
Oh, a tuple is an ordered pair.
I believe.
I hear tuple, I think of like a large quantity or like many.
Finite order list of elements. Okay, so just yeah. So it's any list of things. So this would be like a 2 tuple. So if there's x, y, z, would be a that makes sense. Can you also talk about 9, 10, and 11?
Yeah. Yeah, that's the one I was about to ask too. The 9.
Yeah, that makes sense. You need the bug's position, and you need to know where the birds are.
Yeah, I thought other ones give the exact same information.
Yeah, so it depends on the question, right? If the insects can actually
That's a
move
tuple of bird.
Minimal.
freely in opposite direction, let's say we have 2 insects
How
in this
is
situation.
how's this more minimal?
Let's say one is here and one is here. Now, if this insect can
Oh,
move
this doesn't describe it.
into any of these, and this can move into
Describe what?
any of these. So, sorry. Then we'll end up with all possibilities. If this is not the case, if both have to move in the same direction, then so clearly the number of moves possible is the following. Right? This move is not possible. This insect moving up and this insect moving left. This side is also not possible. But this can go up, this can go down, and so on. Right? So yeah, we should be able to basically construct a situation where both insects will end up in all combinations of places. Right? So
Since all the engines move simultaneously, right?
they do. So both moving, this insect moving this side and this insect moving up is not a valid combination. Right? So they also say the valid actions are basically all the states which lead to 2 insects or more, 2 or more insects in a same square will be just dead ends. So if all other actions are freely available, yeah, we could have places where basically the 2 insects can be in any 2 distinct squares, which is MC2, and then it depends on whether insect 1 is here and 2 is here, or 1 is here and 2 is here, which will bring the K factor. Yeah, I think this is. Of course, an upper bound is always this, which is mn power k. This will clearly be less than or equal to that.
He said question 9.
9 through 11, they're all about the same thing.
So the closest answer would be mn power k in the given ones, because the ones involving other factors are too large, and the ones less than them, would violate this one,
Yeah, that's exactly how I
right?
found
Because in the worst case,
this.
this will be equal to that
This is too small.
when k is 1, right?
This one's too small. And these are way too big.
Now let us see question number 9, which says okay. So basically the insect can share rights with these birds, which move 3 steps at a time. So first question is, which of the following is a minimal state representation, for which basically we need the position of the insect and the time, right? So the answer should be the third one, because all the birds are moving in a very restricted pattern. If we are given the timestamp, we will exactly know where each of the bird is. So that timestamp is sufficient to determine the bird's locations.
Okay.
And the insect location we need to keep track of separately. There is no regularity guaranteed for insects movements.
So you're saying, so you only need the timestamp because that's really how you know what the birds are.
Yeah.
So it's the tuple for each one, or just for the dog, and then just the timestamp to know what the birds are.
Yeah.
So you could, okay, I see what you're saying. So like I was gonna say, like, isn't that interchangeable with just knowing the position and bird stuff? So what you're saying, because there's 2 birds and you have to have
Yeah.
2 positions, whereas if you just have 1 time, you know what both of them are already.
Yes.
So you don't need to track the Boolean of whether or not the bird picked up the insect? Obviously.
That will depend on its position, right? So for each timestamp, basically we will know exactly where the bird is and where the insect is. If it's on top of the bird, then both will be at the same location.
Okay.
Yeah. So how the transitions happen, we don't need to keep track of. What are the states that they go through is what we try to keep track of. And the state is decided by the location of the insect
Okay.
and the bird.
So you can ignore how they're going from each state to each state?
Yeah, so basically if I have the location of the insect and the timestamp, we know exactly where the birds are.
Mhm.
And my actions will depend upon whether they are in the same location or not. And I can choose whether share the right or just move. Based on my action, my next state will be determined.
Okay.
These need not get into the state information.
Okay.
These are the actions available to me depending on the location of the bird and the location of the insect.
So do we need to find or maintain this distance from the current state to the goal, like the Manhattan distance, for minimum space resolution?
So those are not part of state.
Those are not part of state.
Those are not part of state.
Because some of the options had that.
No,
And
that's when the
aspect is
distinction between node information and state information comes. State is about, what can you tell about the world, and node is about for guiding the search. If we want to find a minimal cost path or efficient search, for all these things the G values, H values will add up.
Okay, and we don't have to also bother about the Manhattan distance, right?
That is basically for H value purposes.
That is correct.
So those are not part of the state itself. Those are part of the node.
And how far the agent is from the start state. This is something we can.
That is also again G value, right?
G value.
Which is part of the node information, not the state information. Though, so the state is fixed. G value will depend upon how you reach it. And H value is normally associated with state which is fixed, but it's not itself a part of the state information. Where the insect would be, where the bird is, all those things, doesn't depend on, doesn't care about the H values. We care about H values to solve the problem.
So,
The world itself is just about states.
So time is a state property, not a node property. I guess it would-
So that's what we have designed the state. We have designed the state where we said that, we need to be able to know what will be the location of insect, what will be the location of bird. This is what are relevant to us. So how do we represent it minimally? One is location of the insect we need to keep track of, but do we need to specifically keep track of locations of each of the birds? And we figure out that based on the given information, if we just maintain a timestamp, we'll be able to successfully come up with the bird locations without having to explicitly store them.
It says the birds can move up to 3 squares per time step, so why aren't we considering it when we model?
That depends, that is part of action. So you at each state have options of whether to move simply or whether to share right, based on whether both are in the same location or not. If you take this action, you will end up in a much farther state. If you take this action, you will end up in the next nearby location.
Okay, so that's
So
a
state
dynamic-
is fixed.
Okay.
Your actions will,
It's a dynamic property which we don't have.
yeah, your actions care about that.
Yeah.
What action and what is the resulting state? You will care about those things. State itself need not say that I am in the state, now I have all the opportunity of choosing this. It need not say that.
Yeah.
One can write a successor function which will test that, which is common to all states. Every state need not maintain its own copy of saying, in this state I am open to sharing a ride because I am in the same state. That data need not be stored in the state representation. A successor function can test and tell whether that state is suited for sharing a ride or not. It is night and to control a single insect, you know the maze. You do not know what square the insect will start, so solution all purpose, regardless of industry does not know. Yeah. This is an interesting question. So this is a very nice algorithm, right? This is called rat in a maze problem, which is popular outside AI also, I think. Right? So what does rats do when they are stuck in all sorts of mazes? Basically, they keep moving left or they keep moving right. And when you close your eyes, when you are stuck in a maze which is dark, you can just keep moving right and you will be sure that you will get to one of the exits, if it exists. If there is an exit, you will get to it. Exit, then you will get to it. So which of the following state representations could be used to solve this problem? Position, T, how many time steps, list of Boolean variables, all equations. Yeah, so the key to this is basically how your algorithm will set it. What I am claiming is that when this insect is in a maze, it can just keep moving right, always. When it gets blocked, it turns right and then keep moving right, always, right? So keep moving right, keep moving right, keep moving right, you got blocked, so you turn left. That's the only place where you turn left, whenever you get blocked. Otherwise, you keep moving again. So you get here and you try to move right, you get blocked, so you turn left. You keep moving right, you get blocked, turn left. You got blocked, turn left. Then you come here, you keep moving right, you got blocked, then you turn left. So when you do this, if there is an exit somewhere here, you will definitely reach here. So given that this algorithm works, what do you need as your state information? Do you want to keep track of all the things such as all the squares visited? Do you need it? Given that we know that algorithm just works? No, right? We just need the location of the exit. If it matches to the exit location, we are done. Otherwise, we use this algorithm. Alright, so basically you don't need any of this. You don't need to keep track of all positions. You don't need to have many Boolean variables for each position and so on.
That's the answer.
Yeah, the answer is a Boolean.
And the answer is a list of Boolean variables, one for each position is.
Yeah, so this is a tricky thing.
Here A is not deciding that. Here the path is already decided.
Yeah, so this is the tricky thing, okay? I have put you in a position where I am telling you that there exists an algorithm which will work. If you know this information, then you won't solve the problem to begin with, right? Why do you need to solve the problem? So the assumption is you guys don't know that such an algorithm exists. Then what do you want your state to consist of? Then it makes sense to have Boolean variables saying, okay, this has already been this state, so that you don't get into that and you get into something else. Okay, but this is kind of a tricky problem where there exists such a method which will. But yeah, we don't know that method. If we know that, we wouldn't solve the problem.
Can you briefly just go over belief states? What belief states? Not a question, just like what belief states